Hi, today we're going to be looking at the ratio and root test, the last test for divergence and convergence for BC Calculus. Now, the ratio test is very simple to use. It's one of those, I call it the ain't gonna touch it type of test. Because if we look at a problem like right here, as the series goes from 1 to infinity, 2 to the n over n factorial, I know the nth term test won't work, and none of the other tests will work. Even the integral test, I don't know what the antiderivative of a factorial is, so none of those other tests work. So I have what's called the ratio test. And what the ratio test says to do is I'm going to compare the ratio of the next term over the original term and take its limit. So I'm going to look at the ratio of the next term and the original term. And I'm going to compare it. If that ratio is less than 1, we know it converges. If that ratio is greater than 1, we know it's going to diverge. So if I have a problem like right here, I can just take the limit as n goes to infinity, and I take the next term, so anywhere there's an n, I'm just going to add 1 to it. So 2 to the n plus 1 over n plus 1 factorial. Divide that by the original, 2 to the n over n factorial. Now, it looks kind of complicated, but I'm dividing by a fraction, so I can just invert and multiply. I can write this as the limit as n goes to infinity of 2 to the n plus 1 over n plus 1 factorial times, flip it, n factorial over 2 to the n. And using a little bit of arithmetic here, well, first of all, I know that these two I can just subtract their powers, just a little bit of algebra, and I'm going to get the limit as n goes to infinity. If I take 2 to the n plus 1 over 2 to the n, right? I just get 2, and it goes on top. On the bottom, I'm going to expand this one here. I can make this n plus 1 times n factorial. And if we notice, these n factorials will cancel, and I'm just left with this n plus 1. And I take the limit. Well, the limit here equals 0 as we go, n goes to infinity, which is less than 1. Well, my rule says if that ratio is less than 1, this must converge. So therefore, the series converges by the ratio test. If we try a slightly more complicated one, again, if I look at this one, there's no way I'm going to try to do the nth term test, or the integral test, or even the comparison test. Matter of fact, when I met my wife, I said, honey, you remind me of this series. And she goes, why is that? Because nothing compares to you. Yeah, this doesn't compare to anything. So we're just going to use our ratio test again. So I set it up. The limit as n goes to infinity. Anywhere there's an n, I put an n plus 1. So I get n plus 1 squared times 3. Be careful, if I add 1 here, I get 3 to the n plus 2 over 2 to the n plus 1. And I have divided that by the original term, n squared times 3 to the n plus 1 over 2 to the n. It looks bad, but I can invert and multiply, and we're going to get n plus 1 squared times 3 to the n plus 2 over 2 to the n plus 1 times 2 to the n over n squared times 3 to the n plus 1. Let me rewrite this down over here. I can simplify quite a bit here as n goes to infinity. For 1, if I have 2 to the n and 2 to the n plus 1, I'm going to wind up with 2 to the negative 1 if I subtract those powers. So that becomes a 2, but the 2 is on bottom. Looking at the 3's, again, I'm going to subtract. If I subtract the powers on the 3, I get the n's cancel, and I get 2 minus 1, which is 1. So I get a 3 on top. Now the question is, what happens to the n squared and the n plus 1 squared? Well, I really can't reduce them. I'm just going to leave those alone. So I get this n plus 1 squared over n squared. And I can expand this top here. If I expand the top, I get n squared plus, what's that? 2n plus 1. Now notice the degree on top and the degree on bottom are the same. This is just our Bobo-Botten from pre-cal, right? So I just look at the common ratio. Well, the ratio here is 1, but I'm multiplying it by 3 over 2. So we just get 3/2, which is greater than 1. So therefore, this series, according to my rule, diverges by the ratio test. The last one, go a little bit slower. Kind of help in case you're getting stuck on this one. For the last one, what we're going to do, again, we're going to take the limit as n goes to infinity. Now, what the ratio test says is I couldn't do any of these. I couldn't do any of my other rules. I'm just going to compare. Compare the ratios. I take the ratio of the new term, the next term, which is the n plus 1 term. So that's going to give me n plus 2 factorial over 3 to the n plus 1. I divide that by the original term. So I'm looking to see if this term is getting bigger or smaller. That's all I'm really looking at. So it becomes this n plus 1 factorial over 3 to the n. My algebra says I can invert and multiply. So I'm going to get this n plus 2 factorial over 3 to the n plus 1 times this 3 to the n over n plus 1 factorial. And now I'm just going to solve this a little bit. Now I can expand here. Remember n plus 2 factorial versus n plus 1 factorial. Expand the bigger one. N plus 2, n plus 1 factorial, and those cancel. And what I'm going to be left with, the limit as n goes to infinity, I'm left with n plus 2 on the top. Now, as far as the 3's go, remember this is 3 to the n over 3 to the n plus 1. Well, the n's cancel when I subtract them, right? Because I'm going to subtract. And I get 3 to the negative 1, which is just 1 over 3. So I'm going to get a 3 on the bottom here. And you can probably do that in your head. I'm just going to subtract the powers, the n's cancel. Since I'm left with 1 3 on the bottom, boom, I put it on the bottom there. Taking the limit, we get infinity, which is slightly bigger than 1, just a little bit. So again, because it's bigger than 1, my rule says it diverges. Therefore, this series diverges by the ratio test. And there's our answer. Alright, so if you go to part 2, next one we're going to take a look at the root test, which is really easy. So we'll see you then. Bye-bye.